know that LRT has its wide applicability in testing statistical hypotheses. There are some other tests which are also frequently used in testing different hypotheses. These tests are different with respect to their characteristics in small sample cases, but asymptotically their behaviors are almost equivalent to each other. In today's module, we are going to discuss two such tests which are equivalent in their asymptotic behavior with likelihood ratio test. Let us now consider the following tests having the similar asymptotic behaviors. But before we define the tests, we can start with the following asymptotic aspects. We know from definition of likelihood ratio criteria that lambda x squared equal to capital Lx theta naught by capital Lx theta n hat, where x denotes data from random sampling, theta n hat denotes the maximum likelihood estimator of theta, and theta naught denotes the hypothesized values of theta. So this means minus twice log of lambda x, which is equal to twice small lx at theta n hat minus small lx at theta naught, where small lx denotes the log likelihood. From Taylor's expansion, we can write small lx theta naught is approximately equal to small lx at theta n hat plus theta naught minus theta n hat times small lx prime theta n hat plus theta naught minus theta n hat whole square by 2 times small lx double prime theta n hat. Obviously, small lx prime and small lx double prime denotes the first order and second order derivative of the log likelihood function small lx. Now, small lx prime theta n hat is equal to 0 as theta n hat is the maximum likelihood estimator of theta. So, as a result, twice small lx theta naught minus small lx theta n hat is approximately equal to theta n hat minus theta naught whole square times small lx double prime theta n hat. Or we can say that minus 2 times log of lambda x, which is equal to twice small lx theta n hat minus small lx theta naught, is asymptotically equivalent to root n times theta n hat minus theta naught whole square times minus 1 by n into small lx double prime theta n hat. Now use the fact that minus 1 by n small lx double prime theta n hat, which is actually equal to 1 by n sum over I minus del square del theta square of the PMF or PDF f theta xi at theta equal to theta n hat is equivalent to I function at theta n hat, where I denotes Fisher's information. Hence, we get minus twice log of lambda x, which is actually equal to twice small lx theta n hat minus small lx theta naught, is asymptotically equivalent to root n times theta n hat minus theta naught whole square times I at theta n hat. Again, expanding with respect to theta naught, we get from another Taylor's expansion that small lx prime theta n hat is approximately equal to small lx prime theta naught plus theta n hat minus theta naught times small lx double prime at theta naught. But we already know that small lx prime theta n hat equal to 0 because theta n hat is the MLE of theta, and as a result we get from this approximate relation of Taylor's expansion that theta n hat minus theta naught is approximately equal to minus small lx prime theta naught by small lx double prime theta naught. Or we can say that root n times theta n hat minus theta naught whole square is approximately equal to small n times small lx prime theta naught square by small lx double prime theta naught square. That is equal to small lx prime theta naught square by n times within bracket minus 1 by n times lx double prime theta naught bracket to the power 2, which is asymptotically equivalent to small lx prime theta naught whole square by n times I theta naught square, where I is as usual the Fisher's information. Or we can write root n times theta n hat minus theta naught whole square times I function at theta n hat is asymptotically equivalent to lx prime theta naught whole square by n times I theta naught under theta naught. An alternative way of getting all these asymptotics is to follow the approach of iterative MLE with initial approximation as theta naught itself. Hence, we can alternatively say that minus twice log of lambda x curl equal to twice small lx theta n hat minus small lx theta naught, and that is asymptotically equivalent to small lx prime theta naught whole square by n times I theta naught under theta naught. Also, we can say that 1 by root n times small lx prime theta naught, which is actually 1 by root n times summation over I del theta of PMF or PDF f theta at xi given theta equal to theta naught. This converges to normal 0 and variance I theta naught in distribution. Now, how to justify this asymptotic distribution? Let us define yi equal to del theta of f theta at xi given theta equal to theta naught. Obviously, these yi's for all I from 1 to etc. are IID because xi's are IID, and in this IID yi variables, expectation of y1 equal to 0 and variance of y1 is equal to I theta naught. Hence, by using Lindeberg-Levy central limit theorem, we can easily say that our 1 by root n times summation yi, which is actually nothing but root n times y bar, converges in distribution to normal with mean 0 and variance I theta naught. Hence, the asymptotic distribution is justified. Based on the above asymptotic equivalence and asymptotic normality, we have the following two popular tests. The first one among these is World's test. First, we consider World's test under single parameter case. Here theta is a real valued parameter, and we will reject the null hypothesis H, which says that theta equal to theta naught at level alpha if n times theta n hat minus theta naught square times I theta n hat is greater than chi square 1 alpha, where chi square 1 alpha denotes upper 100 into alpha percent point of a chi square distribution with 1 degree of freedom. Next, we consider World's test under multiparameter case. Here, the vector theta curl denotes S component vector valued parameter where S is greater than 1. Here we reject our null hypothesis H, which says that theta curl equal to theta naught curl at level of significance alpha if root n times theta n hat curl minus theta naught curl prime, the matrix I of theta n hat inverse root n times the matrix I of theta n hat times root n into theta n hat curl minus theta naught curl is greater than chi square S comma alpha, where first of all chi square S comma alpha denotes upper 100 into alpha percent point of chi square distribution with S degrees of freedom. Theta n hat curl denotes the maximum likelihood estimator of the vector theta curl, and the matrix I theta n hat denotes the Fisher's information matrix. Now we will discuss about the another test which is known as rouse score test. Let us first consider the rouse score test under single parameter case. We know that del theta of log likelihood function small lx theta, which is actually denoted by small lx prime theta, is called score function of theta. Also, under the null hypothesis H, which says that theta equal to theta naught, the asymptotic distribution of small lx prime theta naught whole square by n times I theta naught is chi square with 1 degree of freedom. As the justification of this asymptotic result, we can say that we already know that small lx prime theta naught whole square by n times I theta naught is asymptotically equivalent to root n times theta n hat minus theta naught whole square times I theta n hat. Also we know that root n times theta n hat minus theta naught converges in distribution to normal with mean 0 and variance 1 by I theta naught, which is the asymptotic distribution of maximum likelihood estimator. Hence, the asymptotic distribution is directly justified. Now, to get rouse score test, use, due to the above discussion, small lx prime theta naught whole square by n times I theta naught as the test statistic for testing the null hypothesis H, and reject the null hypothesis H at level alpha if the test statistic small lx prime theta naught whole square by n times I theta naught is greater than the critical point chi square 1 alpha. Now we will consider the rouse score test under multiparameter case. Let theta curl be an S component vector where S is greater than 1. Following the same idea as in single parameter case above, here also we reject the null hypothesis H at level alpha if a vector S curl prime, the matrix I inverse of theta naught times again the vector S curl, this quadratic form is greater than chi square S alpha, where chi square S alpha is already mentioned, and the jth component of the vector S curl is Sj, which is defined as 1 by root n times del theta j of Lx theta at theta equal to theta naught. Actually, here we have used the asymptotic distribution of vector valued maximum likelihood estimator theta n hat of theta curl. The rouse score test is also known as the Lagrange multiplier test in econometrics. The test is meant for testing a simple null hypothesis H, which says that theta equal to theta naught, and the rouse score test provides the most powerful test when the true value of theta lies in the close vicinity of theta naught. Naturally, a frequently asked question is why rouse scoring test is the most powerful in locality of theta naught? To answer this question, we know that Neyman-Pearson lemma always provides the most powerful test, and the test can be expressed as the likelihood function L at theta naught plus H given x divided by likelihood function of L at theta naught given x. This ratio is greater than equal to k, and this is equivalent to saying log of this ratio is greater than equal to log of k. Suppose we denote this expression by star. Also, from Taylor's series expansion, we can write that log of capital L at theta naught plus H is approximately equal to log of capital L at theta naught plus H times del theta of log of capital L theta given theta equal to theta naught. Let us denote this approximate relation by double star. Here obviously we have ignored the higher order terms in the Taylor's expansion, as these are negligible if H is very small, that is if theta equal to theta naught plus H is very close to theta naught. Hence, from star and double star we can say that small x prime theta naught whole square by n times I theta naught is greater than some c, where c is chosen that from the size alpha condition. In particular, for large n, c is equal to chi-square 1 alpha, that is a upper 100 into alpha % point of chi-square distribution with 1 degree of freedom, because for large n the asymptotic distribution of the test statistic is chi-square with 1 degree of freedom under H. Note that under single parameter case, the score test does not need an estimate of an information under the alternative hypothesis or unconstrained maximum likelihood. So, the test is applicable even when the unconstrained maximum likelihood estimate is a boundary point in the parameter space. Note that in literature of statistics, the likelihood ratio test, World's test and rouse score test can be referred to as the Holy Trinity due to their wide applicability. All these tests are asymptotically equivalent at least to the first order of asymptotics, but may differ to some extent in the second or higher order properties. As a result of fact, no one test is uniformly superior to the others. This module helped us understand how asymptotics establish equivalence among Elard test, World test and rouse score test. We also studied the merits of applying these tests in the suitable context or the suitable domain of their applications. In this context, we should remember one thing, that these tests may differ even asymptotically in their second or higher order properties.